Good morning and welcome. Thank you for joining us today for the Office of Environmental Health Hazard Assessment's public workshop on the draft cancer inhalation unit risk factor for Isoprene. I'm Dr. Rima Woods, Section Chief of the Air Toxicology and Risk Assessment Section, and I'm joined by Dr. Rona Silva, Staff Toxicologist in the Air Toxicology and Risk Assessment Section. A few logistics before we get started. For attendees here in the room, please remember to sign in at the back table. The restrooms are located out the doors, down the hall, and to the left. And in case of an emergency, please exit at the back or side of the room, proceed downstairs and across the street to Cesar Chavez Park. For attendees listening in via webcast, please send your comments to public.workshop@oehha.ca.gov. Again, that's public.workshop@oehha.ca.gov. And if you'd like to submit written comments, please visit our website at oeha.ca.gov/comments. The public comment period will end on April 2nd. For today's agenda, we'll hear a technical presentation summarizing the draft cancer inhalation unit risk factor for Isoprene. Then we will open the floor for public comments. Each speaker will be allowed up to 10 minutes to deliver their public comments for the record. Comments received from the webinar attendees will be read aloud as well. And those comments can be sent to public.workshop@oehha.ca.gov. And with that, we will start the presentation. So isoprene has the molecular formula of C5H8 and is an alkadiene with 2 double bonds and a methyl group on carbon 2. Isoprene is also known as 2-methyl-1,3-butadiene. Isoprene is a colorless liquid at room temperature with a mild petroleum-like smell and has poor solubility in water. Isoprene is considered a volatile organic compound, or VOC, based on its boiling point of 34 degrees Celsius and its vapor pressure of 550 torr at room temperature. Isoprene is used in making synthetic rubber and is produced through thermal cracking of naphtha. Anthropogenic sources of isoprene include biomass combustion, wood pulping, tobacco smoke, and exhaust from turbine and auto engines. Isoprene is also detected in wildfire smoke. It's emitted by vegetation and particularly by mosses, ferns, and trees, and is produced endogenously in humans and other mammals, and it can be detected in exhaled breath. Isoprene levels correlate with benzene and several other gasoline markers in urban air. Isoprene levels in the air in the US range from 0.6 to 12 micrograms per cubic meter, or 0.2 to 4 parts per billion. In the South Coast Air Basin, here in California, the average concentration in air was measured as 0.5 micrograms per cubic meter, or 178 parts per trillion. And the highest concentration detected was 1.8 micrograms per cubic meter, or 651 parts per trillion. As I mentioned on the last slide, isoprene is found in human breath, and steady state concentrations in end-tidal breath are 195 to 371 micrograms per cubic meter, or 70 to 133 parts per billion by volume, in the 25th and 75th quantile range in adults at rest. Isoprene is listed as a chemical known to cause cancer in California's Proposition 65 program. Isoprene is also classified by the International Agency for Research on Cancer, or IARC, as possibly carcinogenic to humans and reasonably anticipated to be a human carcinogen by the United States National Toxicology Program, or NTP. These designations were based on increased tumor formation at multiple organ sites in rodents exposed to isoprene via inhalation. Following inhalation exposure, isoprene is metabolized primarily through oxidative metabolism by cytochrome P450 enzymes. This process produces epoxide intermediates, which then undergo enzyme-catalyzed hydrolysis, glutathione conjugation, and further oxidation. The main urinary metabolites detected in rodents are listed on this slide, and formation of these reactive metabolites may contribute to the carcinogenicity of isoprene. Three reports containing several studies were reviewed to characterize the carcinogenicity of isoprene in rats and mice by inhalation exposure. The first was a one-year stop exposure study by NTP from 1995. In this study, male rats and male mice were exposed to isoprene for 6 hours per day, 5 days per week for 6 months, followed by 6 months of no exposure to isoprene. And this study had 5 exposure groups and a control group, with 30 animals per species per exposure group. The second report, conducted by Plack et al. And published in 1996, was a long-term carcinogenicity study. Male and female mice were exposed to isoprene for 8 hours per day, 5 days per week for 80 weeks. For male mice, there were 5 exposure groups and a control group with 50 animals per exposure group. And due to decreased survival, male mice in the 3 highest groups were necropsied at 96 weeks, and male mice in the control and 2 lowest dose groups were necropsied at 105 weeks. For female mice, there were 2 exposure groups and the control with 50 animals per exposure group, and the total time on the study was 105 weeks. And the third report from NTP in 1999 was also a long-term carcinogenicity study. Male and female rats were exposed to isoprene for 6 hours per day, 5 days per week, for 104 weeks. And there were 3 exposure groups and a control group with 50 animals per sex per exposure group. Here's the tumor incidence table showing data for male rats from the NTP 1995 study. For these incidence tables, the numerator represents the number of tumor-bearing animals, and the denominator represents the number of animals examined. And the data for male rats show marginally increased incidence for testes adenoma with a positive trend. And the data from male mice in the NTP 1995 report showed statistically significant increased incidence of liver, lung, forestomach, and Harderian gland tumors with isoprene exposure. Whenever possible, OEHA analyzes benign and malignant neoplasms of the same cell origin, both separately and in combination. And for simplicity, the combined tumor incidents are presented here when more than one tumor type was present in the tissue examined. The male mouse data from the Plack et al. Study are shown here. As I mentioned previously, male mice in the 280, 700, and 2200 parts per million exposure groups were necropsied at 96 weeks due to decreased survival. Mice from the control group and the 10 and 70 parts per million exposure groups were necropsied at 105 weeks. Significant increases in liver, lung, and Harderian gland tumors were observed in isoprene-exposed male mice, and these findings are consistent with the tumor sites observed in rats in the NTP stop exposure study. A positive trend for forestomach tumors was observed, but the increased incidence was not statistically significant when compared to controls. And for this study, we were not able to combine incidences of benign and malignant tumors of the same cell type because information was not provided in the publication on if the tumors were observed in different animals. In female mice, exposure-related increases in spleen, pituitary gland, and Harderian gland neoplasms were found. Harderian and pituitary gland adenomas were significantly increased with isoprene exposure. No carcinomas were found for these tumor types. While the increased incidence of spleen neoplasms did not reach statistical significance, these tumors were considered treatment-related. The third report by NTP in 1999 showed significantly increased incidence of kidney, mammary gland, and testicular tumors in male rats, and mammary gland tumors in female rats. In this table, the top value in each cell represents the overall tumor incidence, and the bottom value represents the effective tumor incidence. The effective tumor incidence is the number of tumor-bearing animals, shown as the numerator, over the number of animals alive at the time of the first occurrence of the tumor, which is the denominator. This method of counting tumor incidence removes animals from the assessment that died before they're considered at risk for tumor development. So in male rats, exposure-dependent increases in renal tubule adenomas and adenomas or carcinomas combined were observed with single-section examinations of the kidneys. An extended evaluation using step sectioning of 8 sections per kidney showed an increased incidence of renal tubule adenomas in the 700 and 7,000 parts per million exposure groups compared to control. In the mammary gland of male rats, there was an increase in fibroadenomas or carcinomas, which was significant at the highest dose. And an exposure-dependent increase in interstitial cell adenomas of the testes was also observed in the male rats, with significantly increased incidences in the 700 and 7,000 parts per million groups compared to the controls. In female rats, significantly increased incidences of mammary gland fibroadenomas were observed in all isoprene-exposed groups compared to controls. Studies on the genotoxicity of isoprene have been conducted in various in vitro and in vivo systems. In human cell lines, including peripheral blood mononuclear cells, leukemia cells, and hepatocellular carcinoma cells, isoprene and its monoepoxides were shown to cause DNA damage using the COMET assay. In vitro assays for bacterial mutagenicity were largely negative when isoprene was tested, but positive for the metabolite 2-methyl-1,2,3,4-diepoxybutane. And in mice, inhalation exposure to isoprene induced micronuclei formation and sister chromatid exchange in bone marrow cells. And 3 publicly available PBPK models for isoprene were identified and evaluated to determine model applicability, biological relevance, performance, and reliability. The NTP model was developed for inhalation and intraperitoneal exposure in rats only. The model simulated concentrations of isoprene and its monoepoxides in several tissues, including lung, liver, kidneys, fat, blood, and urine. While this model is relevant for developing internal dose metrics in rats, the lack of human and mouse components precludes its use in this assessment. The Bogards et al. Model was formulated for inhalation exposure in rats, mice, and humans, and included formation, hydrolysis, and conjugation to mono and diapoxides. The model was capable of estimating isoprene concentrations in the lungs, liver, fat, kidneys, and rapidly perfused and slowly perfused tissue compartments. However, model validation was performed only in the mouse and not in humans or rats. The Sanity and Filser model simulated cytochrome P450-mediated isoprene clearance in rats, mice, and humans, and included lung, liver, richly perfused tissue, fat, and muscle. This model lacked components and parameters to simulate isoprene epoxide concentrations in blood and other organs. Since the 3 available models were not fully adequate for use in a quantitative dose-response assessment, OEHOW used the applied dose, or the inhaled concentration of isoprene, as the dose metric for estimating the cancer potency. So there are no epidemiological studies available which examine carcinogenicity for isoprene. There are, however, 3 long-term inhalation bioassays in rodents showing tumor formation in multiple species, both sexes, and tumor induction at multiple sites. Isoprene was positive for genotoxicity assays and is structurally related to the known human carcinogen 1,3-butadiene. Calculation of the average daily dose, or ADD, is a time adjustment carried out to convert the intermittent chamber inhalation exposure conditions to continuous exposure over the lifespan of the animals in milligrams per kilogram day, and will be used to calculate the cancer potencies. The ADD is calculated by multiplying the inhalation rate of the animal by the time-adjusted concentration divided by body weight. The inhalation rate, or IR, for rats and mice were calculated based on body weight using the equations shown here. The average daily doses in the plaque study are shown here and take into consideration the intermittent chamber exposure of 8 hours per day, 5 days per week. And again, the female mice in the plaque study were not exposed at the 3 highest concentrations. The body weight data for the mice in the plaque study were not provided, so standard body weight values for this mouse strain were used in the calculations. The average daily dose in rats for the NTP 1999 study are shown here, accounting for exposure of 6 hours per day, 5 days per week. The weighted average lifetime body weights for the control groups in both sexes were calculated based on the reporting by NTP of group mean body weights during the 2-year exposure. US EPA's benchmark dose methodology and benchmark dose software were used to perform the multi-stage cancer model calculations for Isoprene. A response rate of 5% was used to calculate a benchmark dose, and the 95% lower confidence bound on the dose producing a 5% response was used to calculate the cancer potency factor, also called the cancer slope factor or CSF. Since Isoprene included significant increases in tumors at multiple sites in male mice, male rats, and female mice, the combined cancer potency was estimated using the multi-site tumor module provided in the benchmark dose software. NTP's 1-year stop exposure study from 1995 was not used to derive cancer slope factors because there were 2 adequate studies available that examined the carcinogenicity of Isoprene with a lifetime exposure. Benchmark dose analyses were run for the mouse and rat tumor data that were identified as treatment-related and showed a statistically significant increase above control values and a significant positive trend. For the IUR derivation, data from the Plaque et al. Study showing liver, lung, and Harderian gland tumors in male mice were modeled. Female mouse data were not included in the IUR derivation since only benign tumors were observed. And the male rat data from NTP 1999 showing kidney, mammary gland, and testes tumors were modeled, but the female rat data were not included since the single tumor type observed was benign. Shown here is the benchmark dose output for the kidney tumors in male rats from the NTP 1999 study. The average daily dose is along the x-axis, and the tumor incidence is along the y-axis. The data are represented by the orange triangles, and the blue line represents the dose response curve fit to the data. The black dotted line shows the benchmark dose at the 5% tumor response rate above the control level, and the gray solid line shows the tumor incidence response at the benchmark dose. The vertical yellow dotted line represents the benchmark dose level, or BMDL. And the intersection of the BMDL and the 5% tumor response generates the green dashed line, which is the slope that represents the cancer slope factor for this kidney tumor. Here's the benchmark dose output for the mammary gland fibroadenomas or carcinomas in male rats from the NTP 1999 study. Again, the average daily dose is along the x-axis and the tumor incidence is along the y-axis. And the green dashed line shows the cancer slope factor for this mammary gland tumor data set. And here's the benchmark dose output for the testes interstitial cell adenomas in male rats. Equivalent human cancer slope factors were calculated from animal cancer slope factors by multiplying the animal CSF by the ratio of human to animal body weights raised to the 1/4 power. This scaling accounts for pharmacokinetic differences between rodents and humans, such as breathing and metabolic rates, and pharmacodynamic differences, such as differences in tissue response to exposure. Shown here are the benchmark dose results from the Plaque et al. Study and the NTP 1999 report. The animal cancer slope factor was converted to a human equivalent cancer slope factor using the interspecies scaling described on the previous slide. And the cancer slope factor estimates the excess lifetime cancer risk associated with exposure at 1 milligram per kilogram of body weight per day. The male mouse multi-site tumor analysis for the 3 organs provided a multi-site human equivalent cancer slope factor of 1.47 times 10 to the minus 2 per milligram per kilogram of body weight per day. The multi-site tumor analysis of male rat data in the NTP 1999 study gave a human equivalent cancer slope factor of 1.88 times 10 to the minus 2 per milligram per kilogram body weight per day. And based on limitations of the Plaque et al. Study, OEHA chose to base the IUR for isoprene on the male rat data. Several limitations of the plaque study were considered by OEHA when deriving the inhalation unit risk factor for isoprene. Both benign and malignant tumors were significantly elevated in the male mice, but as discussed previously, the combined adenoma carcinoma data in individual mice were not reported in the study. So OEHA chose to model the data for adenomas, since for each of the sites modeled, the lung, liver, and Harderian gland, the increase of adenomas was larger than that of carcinomas. In addition, individual survival data were not provided, and the appearance of first tumors was not noted in this study, so the effective animal numbers could not be calculated. Based on these limitations, OEHA chose to use the male rat data from the NTP 1999 study to derive the IUR value for isoprene. The IUR was calculated using the human equivalent cancer slope factor derived from the NTP 1999 study. And the human equivalent cancer slope factor is multiplied by the average human breathing rate of 20 cubic meters per day and divided by the product of the average adult human body weight of 70 kilograms and a conversion factor to change the milligram units to micrograms. The IUR for isoprene is 5.4 times 10 to the minus 6 per microgram per cubic meter, or 1.5 times 10 to the minus 5 per parts per billion. Please note the draft document showed an incorrect conversion of the IUR to parts per billion, but will be updated to reflect the correct value shown here. The IUR defines the excess cancer risk associated with continuous inhalation exposure to a given carcinogen at 1 microgram per cubic meter over a lifetime. In the case of isoprene, continuous inhalation exposure to 1 microgram per cubic meter over a lifetime would result in an extra cancer risk of 5.4 in 1 million. And this is for adult exposure and does not include the added risk in children. Once adopted, this IUR will be used in the Hotspots program for calculating cancer risks from chemical exposures resulting from facility emissions. And the draft document presented today is available for public comment through April 2nd. And we encourage you to submit comments electronically using the link shown here. You can also send comments directly to me at rima.woods@oehha.ca.gov. And thank you for your time and attention. And as a reminder for those attending the presentation remotely, you can please send your questions to us at public.workshop@oehha.ca.gov. Thank you.